Good evening. My name is Alyshondria Hicks, and today I will be presenting my capstone project on the automated detection of cardiovascular disease using heart sounds and machine learning. This project explores how combining biomedical signal processing and machine learning can improve early detection and clinical decision making. To begin, it's important to understand the scale of the problem. Cardiovascular disease is the leading cause of death globally, responsible approximately for 19.8 million deaths per year, or about 32% of the global mortality. In addition, it continues it contributes to over 437 million disability adjusted life years, representing a major loss of healthy life. What is especially concerning is that over 75% of these deaths occur in low and middle income countries where access to early detection and healthcare resources is limited. Now, beyond health, cardiovascular disease also has a significant economic impact. It disproportionately affects individuals during their prime working years, leading to reduced workforce productivity and economic strain. In fact, about 80% of cardiovascular deaths occur in developing nations, often decades earlier than in developed regions. However, there is also an opportunity. Research suggests a 20-year window for intervention, during which early detection and prevention strategies can significantly reduce long-term healthcare burden. Additionally, up to 80% of cardiovascular events are preventable, emphasizing the importance of early diagnosis. Despite these advancements, current diagnostic methods still have limitations. Blood pressure measurements, for example, has evolved over centuries, from early invasive experiments to modern cuff-based systems. While these methods have improved outcomes, they often provide only snapshot measurements rather than continuous monitoring. They are also affected by factors such as the white coat effect, where patients exhibit elevated readings in clinical environments. Similarly, traditional cardiac assessment relies on auscultation, where physicians listen to heart sounds with a stethoscope. While widely used, this approach is inherently subjective and dependent on clinician experience. Subtle abnormalities, especially those in low frequency ranges or short durations, can be missed or misinterpreted. To begin speaking about our project, I will start with the heart. The heart has four main sounds, S1 and 2, which are normal and represent valve closures, S2 and 3, S3 and S4, which may indicate abnormal conditions. In addition, murmurs can occur, often associated with conditions like aortic or mitral stenosis. These sounds contain valuable diagnostic information, but they are difficult to interpret manually. In this study, heart sounds are recorded using earbuds, allowing for digital signal analysis. The dataset used in this study was obtained from the University of Toronto. It consists of 15 ACQ files in BioPack format. Each file contains multiple channels of physiological data, including the right earbud, the left earbud, and the PPG signal from the ear, which is a photodiode that is a light signal that you put on the ear. These signals allow us to analyze both acoustic and physiological aspects of the cardiovascular system. Collection process occurred over 3 phases. Day 1, 50 participants were recruited, ages 19 through 69. The data was recorded during 5 minutes of rest and 30 minutes of alternating exercise and recovery. On day 2, 30 patients returned for additional recordings. This captured variability due to diet, environment, and circadian rhythms. Day 3, 12 participants were recorded under controlled noise conditions. This helps simulate real-world environments and test signal robustness. A wide range of features were extracted from the heart sound signals. Of the 247 features, these included MFCCs, which captured frequency characteristics, chroma features related to pitch, spectral features such as centroid and roll-off, statistical features including mean, standard deviation, and skewedness, or a variation of these features. These features also represent both time domain and frequency domain information. This rich feature set allows models to capture complex patterns in heart sounds. The main hypothesis of this study is that machine learning models can accurately detect cardiovascular disease from heart sounds. To test this, we pre-process the data through filtering and segmentation, extracted features from multiple domains, applied machine learning models, and the performance was evaluated by accuracy, precision, recall, F1, and ROC AUC. This slide shows the pipeline used in the study. The process includes signal acquisition, pre-processing, feature extraction, and model training. A supervised learning approach was used in a 80-20 train test split. The structured pipeline ensures consistent evaluation across all models. Several machine learning models were used. The baseline model was the logistic regression, which is simple and interpretable. The two tree-based models, the decision tree, which is rule-based classification, and random forest, which reduces overfitting. And then the advanced models, support vector machine, which handles nonlinear data, and XGBoost and LightGBM, which are high performance boosting models. These models were chosen to compare simpler models versus more complex ones, and interpretability versus performance. Now moving on to the results. We evaluated all models using the same data set and metrics. The goal was to determine which model performed best and whether machine learning can effectively detect disease. This plot represents the cross-correlation between two signals, the left earbud of the first sample and the PPG of the first sample. The x-axis shows the time lag from 0 to 10 seconds, and the y-axis shows correlation strength from -1 to +1. Cross-correlation tells us how similar the two signals are over time and whether one signal leads or follows the other. There's a strong positive correlation near lag equal to 0, as you can see from the diagram, and it decreases as the signal continues. The results show that all models performed in a similar range. LightGBM achieved the highest accuracy of 67% and area under the curve of 75%, making it the best overall model. The decision tree had the best recall, meaning it was best at detecting disease cases. However, no model significantly outperformed the others. This suggests the limitation is likely in the feature representation or the signal complexity and not the models themselves. The ROC curve shows the model's ability to distinguish between classes. The AUC value is around 0.74 to 0.75, indicating moderate performance. The curve is above the diagonal, meaning the model performs better than random. However, It does not match the top, it does not reach the top left corner, meaning there's still room for improvement. In conclusion, my hypothesis was partially supported. Machine learning can detect cardiovascular disease from heart sounds. However, performance is limited by signal complexity and feature representation. The models show strong potential, but are not yet ready for clinical use. In future work, future work, I would like to use multimodal data and apply deep learning models for better performance and improved feature extraction techniques. I would like to thank Dr. Saha, Dr. Mamoun Habib, and the University of Toronto. And thank you for your support and contributions to this project. And I thank you for your time, and I welcome any questions.